Topic of this presentation is IGBT, which stands for Insulated Gate Bipolar Transistor. Let us start with main contents of this presentation, which are Introduction to IGBTs. What are they and how do they work? IGBT design and optimization. How to select, drive, and protect an IGBT. IGBT technologies and applications. How and when to use an IGBT. IGBTs versus other power semiconductor devices. Advantages and disadvantages. IGBT challenges and future trends. How to improve the performance and reliability of IGBTs. IGBT stands for Insulated Gate Bipolar Transistor. It is a type of power semiconductor device that can switch high voltages and currents efficiently and fast. It consists of 4 alternating layers, P-then, that are controlled by a metal oxide semiconductor, MOS, gate structure. IGBT has 3 terminals: gate, collector, and emitter. The gate controls the flow of current between the collector and the emitter, similar to a MOSFET. The collector and the emitter act like a bipolar junction transistor, BJT, which can conduct large currents with low voltage drop. You can see IGBT symbol and structure in this picture very clearly. The working principle of IGBT is based on the biasing of the gate, collector, and emitter terminals. The gate terminal is insulated from the other terminals by a thin layer of silicon dioxide. The collector and emitter terminals are connected to 4 layers of semiconductor material that form a PN-PN structure. When the collector is made positive with respect to the emitter, the IGBT is forward biased. This means that current can flow from the collector to the emitter if the gate is also positive with respect to the emitter. When the gate is positive, it creates an electric field that attracts electrons from the N+ layer to the P layer, forming an N channel. This channel connects the collector and emitter terminals, allowing current to flow through the device. When the gate is 0 or negative with respect to the emitter, the IGBT is turned off. This means that no current can flow from the collector to the emitter. The electric field created by the gate is reversed, pushing the electrons back to the N+ layer and closing the N channel. The device acts as an open circuit between the collector and emitter terminals. There are different types of gate drive circuits that can be used for IGBTs, depending on the application and the topology. Some of the common types are ground referenced gate drive circuit. This is a simple and low-cost circuit that uses a single power supply to drive the gate of the IGBT. The gate is connected to the emitter through a resistor and a diode, which provide a fast turn-off and a slow turn-on. The gate is also connected to the power supply through another resistor, which provides a fast turn-on and a slow turn-off. This circuit is suitable for low voltage and low frequency applications, where the IGBT is used as a low side switch. High side gate drive circuit. This is a more complex and expensive circuit that uses an isolated power supply to drive the gate of the IGBT. The gate is connected to the emitter through an optocoupler or a transformer, which provide electrical isolation and signal transmission. The gate is also connected to the isolated power supply through a resistor and a capacitor, which provide a fast turn-on and a fast turn-off. This circuit is suitable for high voltage and high frequency applications, where the IGBT is used as a high side switch. AC coupled gate drive circuit. This is an alternative circuit that uses an AC signal to drive the gate of the IGBT. The gate is connected to the emitter through a capacitor, which blocks the DC component and passes the AC component of the gate signal. The gate is also connected to an AC source through a resistor, which limits the peak current and voltage of the gate signal. This circuit is suitable for applications where the IGBT is used as an AC switch or in resonant converters. Transformer isolated gate drive circuit. This is another alternative circuit that uses a transformer to drive the gate of the IGBT. The gate is connected to the emitter through one winding of the transformer, which provides electrical isolation and signal transmission. The other winding of the transformer is connected to a DC or AC source through a resistor and a capacitor, which provide a fast turn-on and a fast turn-off. This circuit is suitable for applications where multiple IGBTs are used in parallel or in series. Following are the parameters involved in selecting IGBT. Voltage rating, current rating, switching speed, protection circuits, heat sinks, drive circuits. Some of the ways to protect an IGBT from damage or failure due to short circuit or overcurrent events are: use proper handling precautions when assembling or soldering the IGBT into a circuit. This includes shorting the leads together, grounding the hand and the soldering iron, and avoiding inserting or removing the device with power on. Use a gate drive circuit that can provide the appropriate gate voltage and current to control the switching of the IGBT. The gate drive circuit should also have protection features such as overvoltage, overcurrent, short circuit, and desaturation detection. Use a snubber circuit that can reduce the voltage spikes and ringing across the IGBT during switching. The snubber circuit can be either passive, using resistors and capacitors, or active, using additional switches and diodes. Use a freewheeling diode that can provide a path for the inductive current when the IGBT is turned off. The freewheeling diode should have a fast recovery time and a low forward voltage drop. Use a Zener diode that can limit the gate voltage of the IGBT and prevent damage to the gate oxide layer. The Zener diode should be connected in parallel with the gate resistor. Some of the points to consider when to use an IGBT are: the blocking voltage rating of the IGBT should be higher than the maximum voltage that the application requires. IGBTs are available with blocking voltages ranging from 300 V to 6500 V. The switching frequency of the IGBT should match the requirements of the application. Higher switching frequencies allow for faster and more precise control, but also increase the switching losses and the heat dissipation of the IGBT. Lower switching frequencies reduce the switching losses and the heat dissipation, but also limit the control performance. IGBTs typically have lower switching frequencies than MOSFETs. The trade-off between conduction losses and switching losses of the IGBT should be optimized for the application. Conduction losses are proportional to the on-state voltage drop and the current of the IGBT. Switching losses are proportional to the switching time and the voltage and current of the IGBT. Different types of IGBTs have different characteristics in terms of conduction losses and switching losses. For example, punch-through (PT) IGBTs have lower conduction losses but higher switching losses than non-punch-through (NPT) IGBTs. The diode performance of the IGBT should be suitable for the application. Some applications require a fast and soft recovery diode to reduce reverse recovery losses and electromagnetic interference (EMI). Some applications require a reverse conducting, RC, or shorted anode, SA, IGBT that integrates a diode on the same die to save space and cost. The package and thermal management of the IGBT should be adequate for the application. The package should provide sufficient electrical isolation, mechanical strength, and thermal conductivity. The thermal management should ensure that the junction temperature of the IGBT does not exceed its maximum rating. The main difference between IGBT and MOSFET is that IGBT is a hybrid of MOSFET and BJT, while MOSFET is a pure field effect transistor. This means that IGBT has some characteristics of both MOSFET and BJT, such as high input impedance, low conduction losses, high switching speeds, and high voltage and current ratings. Some other differences between IGBT and MOSFET are: IGBT has a lower on-state resistance than MOSFET, which reduces the power dissipation and improves the efficiency. IGBT has a smaller reverse recovery charge than MOSFET, which reduces the switching losses and the electromagnetic interference. IGBT has a higher gate drive requirement than MOSFET, which increases the complexity and cost of the driver circuit. IGBT has a higher tail current than MOSFET, which prolongs the turn-off time and limits the switching frequency. IGBT has a higher temperature sensitivity than MOSFET, which affects the performance and reliability of the device. The difference between IGBT and BJT is that IGBT is a hybrid of MOSFET and BJT, while BJT is a pure bipolar device. This means that IGBT has some characteristics of both MOSFET and BJT, such as high input impedance, low conduction losses, high switching speeds, and high voltage and current ratings. Some other differences between IGBT and BJT are: IGBT is a voltage-controlled device, while BJT is a current-controlled device. This means that IGBT requires a small gate voltage to turn on or off, while BJT requires a base current to do so. IGBT has a lower on-state resistance than BJT, which reduces the power dissipation and improves the efficiency. IGBT has a smaller reverse recovery charge than BJT, which reduces the switching losses and the electromagnetic interference. IGBT has a higher gate drive requirement than BJT, which increases the complexity and cost of the driver circuit. IGBT has a higher tail current than BJT, which prolongs the turn-off time and limits the switching frequency. IGBT has a higher temperature sensitivity than BJT, which affects the performance and reliability of the device. Some of the IGBT technologies that are available are: punch-through, PT, IGBTs; non-punch-through, NPT, IGBTs; Field stop, FS, IGBTs. Trench gate IGBTs. Reverse conducting, RC, or shorted anode, SA, IGBTs. Here are some applications of IGBT. IGBTs are used in SMPS, switched mode power supply, to supply power to sensitive medical equipment and computers. IGBTs are used in UPS, uninterruptible power supply, system to provide backup power in case of power outage. IGBTs are used in AC and DC motor drives offering speed control, power regulation, and energy conversion. IGBTs are used in choppers and inverters to convert DC to AC or vice versa. IGBTs are used in solar inverters to convert the DC power generated by solar panels to AC power for grid connection or household use. IGBTs are used in induction heating to create a rapidly changing magnetic field that heats up ferromagnetic materials. IGBTs are used in traction motor control and induction heating for electric vehicles, trains, and locomotives. Advantages of IGBTs are as under. They are easy to operate and turn on and off, as they are voltage control devices that require a low gate drive. They have a low on-state voltage drop and power dissipation, as they use conductivity modulation to increase the current density in the device. They have a higher switching frequency than power BJTs, which allows them to synthesize complex waveforms with pulse width modulation and low-pass filters. They do not need a snubber circuit for extra protection, as they can prevent negative voltage and latch-up problems that may occur in other devices. They have a flat temperature coefficient of resistivity, which means they can operate at high temperatures without losing performance. Some of the disadvantages of IGBTs are: they have an asymmetric blocking capability, which means they cannot block high reverse voltages. This limits their use in applications that require bidirectional power flow. They have a lower switching speed than power MOSFETs, which may affect their performance in high-frequency applications. They have a problem of current tail during turn-off, which causes excessive power dissipation and slows down the switching process. They are more expensive than power MOSFETs and BJTs, as they require more complex fabrication processes and materials. Some of the disadvantages of IGBTs are: they have an asymmetric blocking capability, which means they cannot block high reverse voltages. This limits their use in applications that require bidirectional power flow. They have a lower switching speed than power MOSFETs, which may affect their performance in high-frequency applications. They have a problem of current tail during turn-off, which causes excessive power dissipation and slows down the switching process. They are more expensive than power MOSFETs and BJTs, as they require more complex fabrication processes and materials. There are several ways to improve the performance of IGBTs, such as reducing the switching losses, increasing the efficiency, and enhancing the reliability. Here are some tips found. Use a proper gate resistor to control the gate charge and discharge currents. Use a snubber circuit to suppress the voltage spikes and ringing that may occur during the switching transitions of the IGBT. Use a soft recovery diode to reduce the reverse recovery current and charge of the IGBT's built-in diode. Use a thermistor to monitor and control the temperature of the IGBT module. Thanks for watching. That's all for today's video on insulated gate bipolar transistor, IGBTs. I hope you found it useful and interesting. I welcome your suggestions in comment box on what topic you want me to cover. If you want to see more videos like this, please subscribe my channel and click the bell icon to get notified whenever I upload a new video. Never forget to like and share.